Okay, just taking a look at a few more examples. Example 6, we see we have our first definite integral. So in this case, we've got the arctangent of x from 0 to pi over 4. All right, so again, following Liate, it looks like we have a function whose derivative we know, but whose integral we don't. So let's try integration by parts with u equal to arctangent. And then that means dv would have to be dx. So then du is 1 over x squared plus 1 dx, and v is equal to x. So integration by parts yields u times v, so x arctangent of x from 0 to pi over 4 minus the integral from 0 to pi over 4 of v du. So this would be x over x squared plus 1 dx. You can wait until the very end to plug in your bounds, or you can plug in your bounds for this term now and then wait until we do this integral and then plug in the bounds to that one after the fact. Whatever you think is easier, whatever you want to do. I'm going to go ahead and plug it in. So this would be pi over 4 times the arctangent of pi over 4 minus 0. Okay? Now, unfortunately, tangent of pi over 4, we know what that's equal to. That's 1. But arctangent of pi over 4 is not something we actually can figure out, unfortunately. At least not exactly. So this is some gross decimal, so I'm just going to leave this as written. Okay. So now for this integral, this is going to be a u substitution. Let u equal, and this is something that might come up occasionally. Integration by parts is not, as we have said, it's not a substitution method. So although we identify a u and a dv, and therefore a v and a du, these letters don't actually make their way into the result. We really just use u, du, dv, and v as placeholders so that when we think about the integration by parts formula, we put all the right pieces in the right places. So in this case, because of that, we can actually redefine u, because there is no u that persists in our work. This was just to do integration by parts once so that we have this written out. If you'd like to use a separate variable, that's fine. That's fine. I'm going to use u, though, in this case here because it's not contradicting anything. So we will redefine, or let u equal x squared plus 1. So then du is 2x dx, which is 1/2 du equals x dx. Notice that we have an x dx in our integral, so this matches up. So we will replace x dx with a 1/2 du in the next line. Furthermore, we have a definite integral, so we have to change our bounds. So u of 0 is 1, and u of pi over 4 is, well, pi squared over 16 plus 1. So this becomes minus the integral. So we've got 1/2, 1 over u du from 1 to pi squared over 16 plus 1. So pi over 4 arctan of pi over 4. This becomes minus 1/2 natural log absolute u, where u is evaluated between 1 and pi squared over 16 plus 1. So pi over 4 arctan pi over 4 minus 1/2 natural log absolute pi squared over 16 plus 1. And technically we have minus a half natural log of 1, but natural log of 1 is 0, so we have minus 0. So that's the final answer. Okay. Example 7. This is an exceptionally challenging integral. Maybe not exceptionally challenging, but it is challenging until you see an example like it and think to do this. So, for this kind of example, we're actually going to start with a u substitution. So let u equal the square root of x. So then du is 1 over 2 square roots of x dx. Now notice that the function, square root of x, it reappears in its derivative just in the denominator. But because we have defined u to be the square root of x, we can swap out this square root of x for a u. So du is 1 over 2u dx, which we can then solve for dx to find 2u du equals dx. So then this integral here, it's equal to the integral of e to the u, and then dx becomes a 2u e to the u. I'm sorry, not 2u e to the u, 2u du, I mean to say. Okay. So now that we've done a u sub, we are now actually going to do an integration by parts. Because here we've got an exponential function times an algebraic function. So liate, we can let u, well, again, here's where it gets a little tricky, because now we do have a variable u, so we don't want to let u equal e to the u, or u equal 2u. That just doesn't work. Because we actually do have a u here, normally when we write out our u equals equation for integration by parts, there's no contradiction because on this side it's x's. But we can't introduce a new variable to be some function of itself. That's going to be a little bit contradictory here. So just pick a different letter. So let's say w. Right? A w. We'll pick a w for this integration by parts. So this will be the algebraic function, so 2u. And notice here the 2, I didn't pull it out front like I normally do. I'm choosing to include the 2, this coefficient here, with my integration by parts allocation. So I said you can do that. I don't always do that, but sometimes I do. Well, here's an example of me sometimes doing it. So let w equal 2u, and then dv would have to be e to the u du. So then dw is 2 du, and v is e to the u. So applying integration by parts on this, we would have w times v, so 2u e to the u, minus the integral of v dw. So v is e to the u, and dw is 2. So we have 2u e to the u minus 2e to the u plus c. And then since we did a substitution, and this is not a definite integral, we do have to go back to the original variable of x. So finally we can back substitute to get 2 square roots of x e to the square root of x minus 2e to the square root of x plus c. And if you want to factor that out to make it look nice and pretty, you are more than welcome to do that. So we can factor out the greatest common factor, which is 2. So 2e to the x, 2e to the square root of x is the greatest common factor. So this would be square root of x minus 1 times 2e to the square root of x plus c. That's it looking very nice. All right, lastly, example 8. Here we've got an algebraic function and an inverse trig function. So we'll let the inverse trig function be u, since we don't know how to integrate arctan. So we'll let u be the arctangent of x, and we'll let dv equal 2x dx. So du is the derivative of arctangent, which is 1 over x squared plus 1 dx. And then the integral of 2x is x squared. So applying integration by parts yields u times v, so x squared arctangent of x, minus the integral of v, so x squared times du, which is 1 over x squared plus 1, which I will just multiply the fractions and combine them like so. All right. This particular example here, what we can do, this is a fairly familiar trick, but you might not be in the habit of using it yet, but hopefully Calc 2 you will get in that habit. Notice here, in the bottom of that fraction, we've got a x squared plus 1, and the top is nearly the same. So what I could do is add 1 and subtract 1. But I can't just add 1 because that would actually change what we have, but I am free to add and subtract something because really at the end of the day they cancel to 0, and then we just have right back with what we started with. So no harm, no foul. Why would we do that? Well, it's because we can then associate, right? Addition of real numbers is associative. That means we can group things. We can insert a layer of parentheses wherever we want, and it's still valid. So since it's associative, we can do that, and then I can think about splitting this fraction. So I'm going to divide the numerator into this term that I've associated with parentheses, divided by the denominator, minus 1, the other term, divided by that. So I'm splitting the fraction into two other fractions. So this would be the integral of x squared plus 1 over x squared plus 1 dx. And then here we have minus the integral of negative 1 over x squared plus 1 dx. Now, of course, these things simplify quite a bit. This first integral simplifies into just dx, 1 dx. So that's easy to integrate. And then here, double negative, this is the integral of 1 over x squared plus 1, which is also easy because we know that the derivative of such a thing, the derivative of arctan is that. So that means the integral of this, 1 over x squared plus 1, lands right back at arctan. So we have our answer. X squared arctangent of x minus x plus the arctangent of x plus c.